The second thing we're going to talk about today in our notes is just a reminder of inverses. I believe we talked about inverses when we talked about functions, and I believe functions was like unit 3, maybe unit 4 of last year. But inverses, the idea with inverses is that everything is switched, right? So an inverse is what undoes an equation. And so what used to be our input is now going to become our output. So it's this idea of everything just kind of gets switched around. And it gets talked about a lot with cubic functions, especially as you'll see on the next page, graphing the original function and its inverse. So that's why we're just talking about it for today. So everything is switched. So let's talk about things like f of x, which is our original function, and then f to the negative 1 of x, which is our notation for the inverse function. So points, right? If there was a point x, y on our original function, then the point that would be on the inverse function would be our y value now in the x position, and then our x value now in the y position, right? They just get switched around. What is our domain for our original function becomes the range for our inverse function, which makes sense. The range, the domain would be all of these guys, right? Well, now they're in the y spot. So that would be the range. All of our these guys is the range, but it was all of our x values before. Switched around. So then what would have been our range in our original function then becomes our domain in our inverse function. A lot of times we're asked about like, hey, f of a equals b, right? Which means you plug in a for x and it results in a value which is like your y value, right? This would be a point a, b. Well, we know that that point is flipped around, right? It becomes b, a, which means that with our inverse function, if we plug in the b value, we would get a back. So those are some of the things, reminders about stuff that we learned last year, right? But the main idea that I want you to remember is that everything is switched. And especially this guy right here, because that's going to help you when you're graphing with your inverses. And that's what our main focus is with this lesson today and with this unit. If you're struggling on these, remember you've got all of your resources from last year on your archived page on Schoology. So you can always go back to those resources pages and practice your inverses. All right, practicing graphing. All right, so we're going to talk about our original function, and then we're going to talk about our inverse. With our original function, our x-intercepts, go ahead and graph this guy and find the x-intercept. I didn't bring my calculator with me, so I can't show it to you, but you know how to graph it. When we plug this in and we find our x-intercept, which is under analyze graph, and then we go to 0, right? Our x-intercept is not super nice, and there's only 1, and it's 1.26, 0. It's always 0 for our y with an x-intercept. Whereas our y-intercept always has an x value of 0. If we plug that in, hey, notice that would become 0, and negative 2 is what we're left with. That idea with the quadratics last unit, where it was the c value is always right here, your y-intercept. It's now the d value is always your y-intercept, but it's the thing that doesn't have an x on it. Because if we plug in 0, it will be the only thing that doesn't cancel out. So if I were to think about these guys being switched around, and that if this point is on the original function, then the point 0, 1.26 would also be on the graph of the inverse, just flipping around these guys. Notice that 0 then goes in for the x value, which labels it now as a y-intercept, not an x-intercept. Whereas if I flip these guys around, I get the point negative 2, 0, which then establishes it as an x-intercept as opposed to a y-intercept. So with inverses, that's how they flip. But if you just remember, hey, I take the original point and I switch them around, then there's no big deal. You don't. That would be the easiest way to remember it as a consistent strategy for inverses. If you go in and look at the vertices and try and find a minimum and try and find a maximum, you'll notice that as you move your window to look at finding that maximum or finding that minimum, that the point for the TI Nspire is that the point that signifies that maximum travels with the window, which means that there is no maximum and there is no minimum with this graph. This graph looks something like this. It doesn't look like this, right? It does not look like that. It looks like this. Sometimes our cubics don't have a maximum or a minimum. It's always increasing from left to right. It's always increasing. It just never actually, yeah, increasing, decreasing, increasing. It's always increasing. It just gets less increasing in the middle, but still continually increasing. So you don't have to have a vertex with a cubic. Sometimes there are none, but the only way you find out that there are none is if you go in and look for the maximum and you're like, the point for maximum just keeps following my window. It just keeps telling me it's right at the edge. So just make sure that you're paying attention to that. So for this one, we have no vertices. Since these guys are not super nice points, well, at least one of them is not a nice point, and I don't have any vertices to really go off of, I really only have 2 points, I'm going to grab some additional points going on around this. So additional points. So I want you to finish the following points. I want you to find out what is the y value when x is -1, when x is 1, and when x is 2. So if you just hit trace and plug in -1, enter, you'll get -3. If you hit trace, press 1, enter, you get -1. 2 then has an x value of 6, or you could just plug them in here. -1 cubed is -1, minus 2 is -3, 2 cubed is 8, minus 2 is 6, right? Pretty straightforward. If I want to take those additional points and move them to my inverse guy, the inverse of the original function would have the point not -1, -3, but rather -3, -1. The point 1, -1 would become -1, 1, just switching them. This guy would become 6, 2. And now I'm going to graph them all onto one graph page. With inverses, your axes, it's just a lot more to think about. But just take a look at all of my y values. 0, -2, -3, -1, 6, 0, 1.26, -1, 1, 2. The highest number I get on my y-axis is 6, and the lowest I get on the y-axis is -3, which means I don't need as much down here. I only need to get to -3, and I only need to get to 6, which actually means that, like, yes, less space in the negative because I only need to go to -3. But also, I don't need to worry. I'm not going to run out of space if I go by ones here, right? If I go 1, 2, 3, it'll definitely be easy. 1, 2, 3, 4, 5, 6, definitely easy. Yeah, so let's put it, our x-axis, something like this to account for that, right? Y-axis, looking at all my x values, where should I put it in order to account for all of my x values? 1.26, -1, 1, 2, same thing, right? Which makes sense because we're talking about inverses. So we're going to, whatever is going on in the x's is also going to be going on in the y's in some way. 6 is the largest value I get up to on the x-axis, and the smallest one I get to is -3. And so I'm doing the exact same thing over here. You could mirror it, it'll look nice, or you could just put it in the middle and it'll be fine. Go ahead and label X and Y. I'm also going to number it off. 1, 2, 3, 4, 5, 6, 7. Cool. Then I go in and do my original points for f of x. 1.26, which will be here, 0, and then 0, -2. Some of my additional points. And then looking at the graph that we made, which will be helpful in grabbing all of these points so we can label them, we can also now use the graph that we looked at on our graphing calculator in order to look at the general shape. It's kind of got these dancing arms, so I kind of figure out the dancing arm middle part first, and then I try and adjust for the part that shoots up to the end. Put an arrow here and an arrow here. Just general shape. But make sure not to make it a straight line. You need to have it be curvy because that's what this graph is. I'm going to label it f of x because I'm going to go in now and find my inverse. And my inverse would have the points here. So by doing these point flips on your own before graphing it on the graph paper will kind of help keep things straight. And so then that way when you're making the graph, all you have to think about is just connecting the dots, right? It's still got the little arm wave and then it shoots up in the end. Arrow, arrow. And this is the inverse. This is how the graph of an original function looks like compared to its inverse. If I were to draw in the line y equals x, which I don't know why I'm struggling with that. There we go. Ish. Y equals x, think about it as mx. Oops. Think about it as mx plus b. M is 1, b is 0. So y-intercept of 0, up 1, over 1 as our slope. The equation of the original function when compared to its inverse is always going to be reflected across that line. So it's going to look like a mirror image. And where they intersect will be also where they intersect with the line y equals x. And it's because whatever point that is there, the x value and the y value are exactly the same. It's the only place where my input and my output have the same number. So when I flip them, it's doing the same thing. And that's how we deal with graphing inverses. I would like to challenge you. I won't do it again with you. But I would like to challenge you to do this on this next one on your own. Follow that same process, and then I'll go ahead and come back from your homework and ask to see, when I'm checking your homework, that final graph. So you're going to do this on your own. There's going to be no more video, and you're going to practice graphing these cubics on your own. If you have any questions, go back and review the process that we did together in this video. All right, good job.